Hi everyone, the last of these probability inequalities is Minkowski's inequality, which is essentially a triangle inequality for the norms of random variables, as we'll see in a second. So the theorem is Minkowski's inequality. And it says the following: let P be a real number at least 1, and assume that we have random variables x and y with expectation of P's moments finite. E of x to the P finite and E of y to the P finite. Then the statement is that the expectation of the sum of x plus y raised to the p power, and then taking a 1 over p power around the expectation, is going to be bounded from above by the sums of similar expressions. So p's moment of x to the 1 over p power plus the p's moment of y to the 1 over p power. And before proving this theorem, so that's the statement, before proving this, let me again mention that actually this combination here is sometimes called the P's moment of the random variable x, and this is called the P's moment of the random variable y. And then of course on the left we have the P's moment, P's norm, not moment, norm, P norm. So these are P norms of x plus y, and what we see here is actually the triangle inequality. Homework for everybody: when I said Cauchy-Schwarz inequality, when I told about Cauchy-Schwarz inequality before, you could rewrite that in terms of these two norms and convince yourself that the Cauchy-Schwarz inequality we've seen in terms of random variables has actually the same form as Cauchy-Schwarz as you have seen it for vectors using these two norms. Okay, so this is like a triangle inequality for the norms. Let's prove it. The proof will consist of 3 steps. Step one is a calculus lemma again. We're just doing a little bit of calculus. Fix A, B positive numbers and P at least 1, actually strictly bigger than 1. Why do I fix P strictly bigger than 1? Because when P is equal to 1 is actually a trivial case. When P is equal to 1, an expectation of the mod of the sum is of course more than or equal than the expectation of the mod of x plus the expectation of mod of y, as simply shown by a triangle inequality for mods. So let me just add here that P equals to 1 is trivial, just a triangle inequality and an expectation applied on that. So I'm going to assume that P is strictly larger than 1, and I'm going to consider the following function. F of x is going to be a plus x to the power p minus 2 to the p minus 1 times a to the p and x to the p added up. This is a particular function I'm going to look at, and let's differentiate this function. So let's make a little bit of analysis on this function. If I differentiate it, then of course I get p, so this is equal to p times a plus x to the p minus 1 minus 2 to the p minus 1 and then p times x to the p minus 1. Alright, I'm differentiating with respect to x. And now I want to look at this formula I got for f prime of x and conclude the following: not equal. This thing is going to be first of all, let's actually look at the equal case. It is going to be equal to 0 if x happens to be a. That's the first thing I want to emphasize. So why is that? If x is a, then I have 2x here to the p minus 1, so it's 2 to the p minus 1 times x to the p minus 1 times p, and here I also see 2 to the p minus 1, x to the p minus 1 times p. Those cancel and I have 0. If a happens to be larger than x, then from that 0 I'm moving off to the positive direction, so then f prime is positive. And if a is smaller than x, so x is larger than a is smaller than x, if a is smaller than x, then from that 0 this term will dominate less and this term will be larger relative to the first, and that moves f prime to the negative direction, so then f prime will be negative. So here I have a function that has a positive derivative below a, it has a 0 derivative at a, and it has a negative derivative above a. And also, if I look at the function itself at a without derivative, just the function at a, what do I see? I see 2a to the p from the first bit, a plus a to the p, minus 2 to the p minus 1 times a to the p plus x to the p, so that's a 2a to the p. Again, terms cancel. I have 2 to the p, 2 to the p, a to the p, a to the p, they cancel, and I get a big 0. So I have a function that's 0 at a, its derivative is positive before a and negative after a, so actually it reaches its maximum at a, which is 0. So for any other points other than a, the value of f has to be less than f of a, has to be less than 0, and therefore I conclude that f of b being a plus b to the p minus 2 to the p minus 1 a to the p plus b to the p is negative. It's actually strictly negative. Actually, I don't need strict, it's enough to have smaller than or equal. And if I rearrange this, then I have this very useful conclusion of step 1, that the p's power of a sum is always less than or equal to 2 to the p minus 1 times the sum of the p's powers. This is what I aimed for in this step 1. Okay, so that's the first move, that's the first step I want to make. Let's keep this in mind and let's see how I can use this to proceed with my proof. Okay, so page number 2, and then let me apply that inequality, the conclusion of step 1, let me apply this one on my random variable x and y. So that tells me that the mod of x plus y to the p's power is less than or equal to the p's power of the mod of x plus the mod of y. No, sorry, that's not what I want to say. That's only my first step. Okay, so I'm looking at the p's power of the mod of the sum. It's just a simple triangle inequality at this point. This is just a simple triangle inequality at this point, that this is smaller than or equal than the sum of the mods to the p power, and now comes my lemma. So I'm going to actually apply the calculus step 1 on x mod and y mod. So x mod and y mod to the p's power smaller than or equal 2 to the p minus 1 x mod to the p plus y mod to the p. That's what I want to really use this calculus lemma for. So this is already actually step 2. I forgot to put here step 2. Okay, so step 2 is that when I apply the lemma, then I apply step 1, then I can bound the p's power of this sum by 2 to the p minus 1, the sum of the p's power. 2 to the p minus 1, sum of the p's powers. X to the p plus y to the p. Okay, why is that helpful? Why did I do all of that? Because I actually don't know a priori that even my left-hand side makes sense. I don't know a priori that the expectation of x plus y to the p's power is finite. But now I can actually say that, because I know that the expectation of 2 to the p minus 1 and then x to the p plus y to the p is, of course, equal to 2 to the p minus 1 times e of x to the p plus e of y to the p, both of which are by assumption finite. So the conclusion of step 1 is that the expectation on the right hand side is finite, and that implies that the expectation of x plus y to the p is also finite. Okay, so that's the conclusion of step 1. Expectation of x plus y to the p is finite. This is why we did the calculus first step, and this is why we then applied it to the random variables x and y. Okay, so this was the second part of the proof, and then let's do the actual inequality. Let's do the actual Minkowski inequality. So step 3 on page 3. Step 3 goes like this. So now I want to start with the expectation of x plus y to the p power, and the first thing I do is I'm going to separate one of these x plus y's. So x plus y mod and x plus y mod to the p minus 1. This is my first step. I'm going to apply a triangle inequality on x plus y. Mod of x plus y by triangle inequality is smaller than or equal than the mod of x plus the mod of y. Okay, and the rest here is non-negative, so therefore this whole right hand side is less than or equal to the expectation of mod x plus mod y multiplied with the p minus first power of mod x plus y. Okay, now comes Hölder's inequality, but Hölder's inequality needs to make sure that the expectation of okay, we'll see in a second. It needs to make sure that the expectation of the p's power or some power of the first term and the corresponding other power of the second term is finite. Now, what are these powers? What are these powers? So I'm going to introduce to this p, which is larger than 1, I'm going to introduce q. Let q be p over p minus 1. Why is this choice of q? Well, actually, if I look at 1 over q, that's going to be p minus 1 over p, or if you want 1 minus 1 over p. So in order to, the reason I picked this q is that 1 over p plus 1 over q is exactly going to be 1 under this choice. So I'm going to make this choice of q, okay, and then I'm going to apply Hölder's inequality on this quantity here with actually in two parts. So let me just do one more step here. Expectation of mod x times the p minus 1 power of x plus y, and expectation of mod y times the p minus first power of x plus y. This just using linearity of expectations. And now I'm in a position to apply Hölder's inequality. Okay, I'm going to take the p's power of this first term and the q's powers of the second term, and that's how I'm going to use Hölder's inequality. Now the q's power, so let's do the q's power of the second term, x plus y to the p minus 1 raised to the q power. What is that? So q is defined to be p over p minus 1, and if I raise the p minus first power to this, then of course the p minus 1s will cancel, and I have x plus y to the p. So when I apply Hölder's inequality, then out of this x plus y to the p minus 1 term will come x plus y to the p. However, the only way I can apply Hölder's inequality is that I have a finite mean of this thing, and this is exactly where step 2 comes into play. The expectation of x plus y to the p power is finite, so Hölder's inequality is justified, and I can apply Hölder's, and that tells me that, so Hölder tells me that this right hand side is smaller than or equal to the expectation of the p's power of x on the 1 over p power times expectation of the q's power of x plus y to the p minus 1, but that's what we calculated here, so that gives me x plus y to the p on the 1 over q power. And again, the reason I put that here is that if I raise x plus y to the p minus 1 to the q power, that gives me x plus y to the p. And then I have the similar term for y, expectation of y to the p on the 1 over p power times expectation of x plus y to the p on the 1 over q power. Okay. Now, what is 1 over q? What is 1 over q? 1 over q is 1 minus 1 over p. Okay, so this guy here is 1 minus 1 over p. So now what I'm going to do on the two sides of this inequality, I am actually going to multiply through by expectation of x plus y to the p power raised to the 1 over p minus 1 power. So I'm just going to actually divide by these second terms. I'm just going to divide by these second terms. And then what is going to happen? So I have expectation x to the y to the p. Let me put this here again on the left hand side. Expectation of x plus y to the p. All of this raised to the first power on the left hand side. I'm going to divide through with the second terms. So that gives me a minus 1 power here and the plus 1 over p power. Smaller than or equal, this is all positive, so the inequality doesn't care. I divide it through by the second bits of both terms, so all I have left is expectation of x to the p to the 1 over p power from the first term, plus expectation of y to the p to the 1 over p power from the second term. On the left hand side, 1 minus 1 cancel, and I have just the 1 over p's power on the left hand side of the p's moment of x plus y, and then I have the 1 over p power of the p's moment of x and the p's moment of y respectively, and that's exactly what I need to conclude the statement. That's exactly what I started with in the statement. Expectation of x plus y to the p to the 1 over p smaller than the sum of these similar terms. That's exactly what I have done there.